where it comes from. It's the early understanding of the availability or unavailability of commodity crops. And there are two branches essentially of users. One is on the side of food security or food insecure regions, where you can have an early warning and early understanding of an upcoming difficult situation. And the other side is more on the market side, commodity market information. Now, how does it look like? I mean, you shouldn't read out this here. Just to be clear, this is a crop yield forecast of 1 month that we produce at JRC every month. And essentially, you see information on area, on yield, and production that goes together. Here now, today, we talk about the yield estimates comparing to last year's differences and so on. That's what we publish, and these are the figures which are used. Of course, you can also present them in a nicer way to understand them spatially at national level. But this is not unique to the JRC. I mean, there's the USDA producing similar information. You see area harvested, yield, production, well, different units, obviously, again, forecasted last year. Yeah, this is information from the Crop Estimates Committee from South Africa. Again, 2 points of forecasting of production with areas, so you can also get the yield out of that. And last but not least, also the Chinese Crop Watch Bulletin is producing estimates even for other parts of the world, not only China. Here we have the example for Argentina and Brazil expressed as yield changes. But in the end, you see there are many institutions doing this on a very regular basis. And of course, you might ask, well, who's interested in that information? There are several players. I mean, there are market players that, of course, are interested in producers, traders, brokers, food processors, investors that are interested in this early information. Then there's a group of, I would call them market observers. For example, there's actually a G20 initiative of the Agricultural Market Information System at FAO to increase transparency. There's the International Grain Council producing estimates, and there are private companies like the large Strategy Grain, which have that as a business model. So there are different that produce and are market observers. And then there's the third category of market management. Well, that's national governments, or in our case, the European Commission, that looks at production and demand and production and trade relationships. And then, of course, there's the other side where just the management of emergency situations, combating food shortages, NGOs, World Food Programme, national aid agencies. So there are several users that look at this information. And if we analyze I think that's 2016, the users of our bulletin, of our Mars bulletin, you see it's from government, news producers, business, from goods and supply, trade, information services, and then also research. You could say it's a good third, which is business, 1 quarter, which is government, and another third that is research looking at this information. That's quite interesting. And in terms of quantities, I mean, we have about April, May, June, which are the main bulletins, main important ones for Europe, obviously. We have users about 2,000 plus that download the bulletins within 1 or 2 days after publication. So, there seems to be quite an established community of producing this information and of using that information. Now, what are the requirements for this crop yield forecast? Timeliness is probably one of the most important. That means you have to produce on time. And actually, that's again an example from South Africa. We all publish calendars by when you can expect the next forecast. That's what we do for Mars in Europe, and that's what the USDA is doing. So this information is expected on the day, and I can tell you, if it's not there, your email box is full of complaints that people are waiting for this information to come up. Another requirement, accuracy. Well, yes, of course, the forecast should be as good as possible, but how you evaluate, I mean, if you compare the production estimates compared to statistics that come then later on available, you see we are getting quite close. We are within the typically 3 to 5% margin. And again, that's probably not particular only to us. If you divide it by crops, then you see there are some crops which we do better in some years than others, but it's all within 4% of error compared to the statistics at EU28 level. Yeah, it works. Then reliable and transparency. That's, I think, an important point to build trust in your information. So most of the systems publish their methodology how you produce this forecast. There's a whole list from USDA documentation how the forecasts are produced. There's an overview document, quite a nice one, looking at 3, 4, 5 systems existing. That's from 2016, done at FAO overview. And we have actually a wiki for our mass crop yield forecasting system online. So that information is available. So we try to be transparent, at least the national systems, probably not the private ones, if that's their business model. But transparency is really one asset here that gives trust to the figures that we produce. And then one particular figure, and that's probably different to any crop model simulations and the climate change context. We know if we are wrong or right tomorrow. I mean, at the end of the season. So if we now publish a forecast in April, at latest in October, we know if we have been good or not. And it's not only us, also the others know if we are good or not, and they let you know. So, I mean, that sounds quite a strong, motivation, but it also is very useful to learn from your exercise. So, of course, then we look at our yield forecast. Here you see it's grain maize for Austria, for example, 2016, and from March to November, the monthly forecast, and you show the differences in absolute tons per hectare. And we start off with almost 1 of the observed yield, which is the black line, and then the points approach closely when you go along the season to the real yields. Now, what you can also see there, the first 3 months, the values are the same. So here, obviously, there's nothing on the field for grain maize in Austria. So we do statistical forecasting based on whatever. It's not only yield. So there might be changes in the area, and then you get different production estimates. And the last 3 months are, again, once we reach maturity, of course, we don't change the forecast anymore. But you also get these kind of behaviors where we start conservative on the statistical side. And in the beginning of the growing season, we are very optimistic. We overestimate. And only in July, in this case, Bulgaria, for grain maize, we come down. And probably there was some event, some drought or some heat wave, whatever, that made us going down with the forecast and getting into the right range. So that's the part on verification, what you can do easily there. If you do it aggregated for grain maize in EU28 for the 2016 season, then you see that we start with a deviation of 0.38 of tons per hectare, and we end up with almost 0.08 tons per hectare. You see also the uncertainty is increasing in May, June, and then decreasing. So once we get out of the statistics into real looking at crop parameters, we first get a larger spread, and then we narrow down when it comes to the crop growing, to the final of the crop growing season. So what sources of information are typically used for in-season crop monitoring? Well, I mean, there's the whole range from statistics surveys. I mean, statistics, simply you have the timeline of the last 20, 30 years, and you, well, assume maybe some technological trends. Surveys, if you're lucky, you get from the farmers direct information, but we have in Europe 10 million farm holdings, so that will be a bit difficult to get that all on board. Agrometeorology is a classical one. Obviously, you look at temperature development, derive agromet indicators like temperature sums or like climatic water balance, water deficit in certain periods. Remote sensing is very much used. I come back to that. High spatial resolution of a similar method covering large areas. And then there's crop models, crop growth models. And last but not least, and that's probably one which is most used, is the expert judgment, because all this doesn't give you the real yield that you want to forecast, but give you indications in which direction you should go with your forecast. And in the best case, you get a convergence of evidence of these sources of information here. Now, if you see examples, systems, what methods they use, I mean, for the statistics and surveys, the NAS, for example, also the South African system is using surveys. Also, the Ministry of Agriculture in France, we had a nice comparison. They're using surveys and are, you know, compared to our forecast, better later in the season. But before they have the surveys, we are a bit better. So that's quite interesting activity. Agromet is used by many systems, Mars, CropWatch. Remote sensing then, okay, there's the FAST systems for outside US, which based also on remote sensing Mars. The ASAP is a system at JSC, not producing quantitative crop forecasts, but it's for the food insecure regions and saying if you go below a certain threshold, then we set out an alarm. CropWatch is the Chinese system, strongly based on remote sensing. Moroccan system, remote sensing. Then crop models, you don't have so many systems that are based on crop models. Essentially, it's our Mars system and some, the Belgium CGMS is has started from the Mars system, further developed at national scale. Morocco and also the Grain Crop Institute in South Africa uses some crop models. Not sure if that's really in the operational process, but that's close to it. But all of them, and including our private institution, use expert judgment, that's for sure. Now, how does it look like? I mean, very briefly only how we use it in our system. There's the weather information, what we call the meteorological infrastructure, the crop growing simulation, crop growth simulations, and the remote sensing. That are three more or less independent sources of information that come into the analysis, and that brings us to a qualitative forecast. I mean, besides the forecast, you have also country analysis and description of hazards and of adverse weather situations that require this information. But to come up to a quantitative yield forecast, we don't rely on either of the single factors, but we use indicators from each of these infrastructures in order to infer a quantitative analysis matching against, in regression, for example, against the time series of yields that we have available from the past. And that's where the expert judgment comes in. And if you want to look at it from another point of view, you have the maybe there's even a beamer. Oh wow! There's the crop development along the growing season, and to a certain degree you have observed weather. You might have a short period of a weather forecast, but then it ends, and so also your crop growth simulations will end at the same time, and also the remote sensing ends at the T0, obviously. So how do you bridge the gap to come to a yield forecast at the end of the season? And that's where the statistical analysis goes in. And interesting, if you analyze, and that's what we are doing also, basically, what methods we use to bridge this gap. Then it's difficult to read by distance, but what you see, the green and yellow bars are essentially trend analysis, and that's early in the season. And the brown and blue ones are regression analysis based on indicators that we produce for the crop models, with remote sensing and with AgMIP. And of course, at a certain time in the period, they take over and are used for crop modeling. And that timing, of course, depends on your crop region season combination, and that is quite diverse. Now, why using a crop model in that context? I mean, that's now the point. And it integrates, as we all know, I mean, various information. It's the static information, soil, crop mass, if you have information on technology, cultivars for the calibration, and the dynamic weather input, remote sensing maybe. It follows, and that's, I think, the important part, biophysical processes. You have cause effect relationships built in the model. So if you have a deficit in precipitation in your AgMIP and you have below average NDVI in remote sensing, it could relate, but from those two sources, you don't know if it does indeed. Maybe you look at another crop than you think, or maybe the sowing date was 3 weeks later than you expected. So you're below the average development. So you need the crop model to be sure on the mechanisms to explore them. Then, of course, it produces variables that are not observed. So that's where you can analyze, and it keeps a memory. You tend, in these processes of yield forecasting, look at the current events. The current drought has it an impact, but you easily forget that early in the season we had very favorable situations, warm and wet, and crop is above average development, and the 2 weeks of drought we can easily compensate. So that's also what you get with the crop model information. And well, I mean, that's just examples of output. I mean, that's for regional output, for some parameters that come out of the crop model that we make available to the analysts in near real time. So relative soil moisture, where you see, the middle line is the average conditions, and then some standard deviations. And you see at a certain time in the period, we go far below the average conditions. You have here the water limited leaf area index in Hungary. You have information. Well, on crop development stage, what you get out of the crop model, or about water-limited water storage organs, where you also have quite an early positive development, but then that leads obviously with quite warm situations and dry situations in Spain, leads to an early finish of the crop cycle, and of course reduces the yields. So that's information that we derive from in our system from our crop models, and that we consider quite valuable. Now, what are the situations in which we think crop models are extremely useful? Water deficit, we have heard, overwet situations is quite critical for us in Europe, and we are not very good on that. So that's something, but no remote sensing would help you with that. Heat stress, we heard often this morning. We have often situations that yield and biomass development is diverging, and what you see with the remote sensing is biomass. So also there, crop model helps a lot. Pest and disease is quite a challenge, but also including, if you know about practice like irrigation schemes, something like this, you can include in your crop model. But there are also drawbacks. It doesn't come for free. I mean, it's clear we know crop models are essentially point models, and calibration. The calibration for gridded crop models is limited, and that's what we work with. And there is, of course, the point that what you get out of the crop model directly is not what you are looking for. So you need to detrend your real yields for technological trends, and you need to search for the variability that is induced through weather impacts on your yield. Then, of course, there's some other point in practical use. In near real-time mode, you need to be able to process all that in short time. For example, I mean, if in our case, monthly bulletins, we have 1 week per month where we do our forecast, our analysis. And from you want, of course, to use the most recent information available from all the data sources. And so we have, in the end, 2 days maximum for all the processing until you make the information available for the analyst in a digestible form. And that must be feasible. It is feasible for us for a crop model 1, 2, 3. You probably could do more, but you need to invest in that as well. Now, what all does it mean for AgMIP? I mean, what's in here? And obviously, many of the aspects that I've mentioned are already addressed in AgMIP. And I just put here a list, which we heard this morning already, so I don't want to repeat that. Evaluation of crop models, which is a better one to use. Calibration, improving model processes, heat stress, we have heard, very important for us. The issue of ensemble crop modeling was mentioned several times. Gridded crop models, we have some experience in AgMIP. So, I mean, all these things, scaling, results of scaling is quite important for national forecasts. What scale do you work, input data, soil data. So all these topics are treated, and it would be a pity not to exploit and to use them in this context, but that's what we think. Now, obviously, you need to evaluate them against the specific requirements of this activity. And the core question is clearly, I mean, do the crop model improvements that we have done really improve the final crop yield forecast? And what are the relevant findings that we could use, and how robust are that in all the situations we have to produce a crop forecast? And that's why we propose to have a working group on seasonal forecasting. And we had the first session yesterday, and we're brainstorming a bit what could be done, and that will be more go on tomorrow and come to more concrete questions how to go ahead. But I mean, hindcasting of critical situations that we know are surely a good point how to go ahead. And now, in our case, I mean, we already use crop models, so we see some potential to improve that. But I think we should go far beyond the few groups that are within AgMIP. But once we have some tangible results and proven added value, we should reach out to all these groups that do not use yet crop models. They're based on remote sensing, based on statistics, and approach them. And that brings me to one discussion which also we discussed yesterday. It's the synergies with remote sensing. I think that's something we really should look at. Remote sensing is quite prominent in crop yield forecasting. It's technology driven. There's recently the Copernicus program with all the Sentinel satellites promising high resolution in space and time. And that's really quite an opportunity. There's a lot of US programs, MODIS as the working horse. And there's a new full generation of satellites from China upcoming, already in place partly. Perfect, 2 slides more. And The second thing, remote sensing is moving away from the traditional indices towards biophysical parameters. Also, that helps us much more to get in touch with them. Now, the remote sensing community is a bit like the crop modeling community. It's easy to go from your remote sensing world to yield directly, like we use with our crop models going directly to yield. And I think most promising, however, would be the joint use of this information. So combining the process orientation of the crop models and using the highly resolved spatial information that you get from remote sensing. And we have identified yesterday, and I put it already at it first early on the slides already, 3 opportunities. I mean, the mapping of where is which crop is unique for remote sensing. And that's where we can, of course, benefit from where do I model my wheat, where do I use my wheat model. But then, I mean, the spatial resolved input parameters is something which is probably also well feasible. It's happening already partly. In our case, global radiation, snow cover, sowing dates, initial soil moisture, all this spatially resolved information could be well used even in a near real-time context of in-season forecasting. And then probably more on the research side is the assimilation of remote sensing derived parameters. There's a lot of research ongoing, but I haven't seen really an operational application that is working. So that's a challenge. And so there, I clearly would encourage the further exchange with the community. And one to mention is the GeoGlam community. Actually, they met last week in ISPRA, defining the further needs for satellite data. And there I made the point already that I will be here this week and seeing the way to collaborate together. And I think there is also some interest in the partners are given here. It's the partners themselves with their institutional work, but it's also ongoing projects that they are executing, like in Belgium, the Belcam project, the EFSAC in the NASA, new NASA program of 50 million. Some of you would be involved there, supporting the US GeoGlam activity within the US and has an international component. And last but not least, the DBAR, the Digital Belt and Road Initiative in China, which is supporting strongly, for example, the further development of the CropWatch bulletin based on remote sensing, but they are equally see the need to get into crop modeling. Actually, we had a one-week training for them in March in ISPRA for a group from Radi, from the Institute of Remote Sensing Applications, from the Academy of Science. And I think there are many players now finding the 2 lanes, and I think that's a good moment to jump into that game. So concluding, seasonal crop forecasting is happening every day, every month in many places of the world, and there are users using this information. They hardly make any use of crop models. So with all the knowledge we have in AgMIP, shouldn't we help that community? Is there not something in for us to have a spin-off of our results on the practical, on the day-to-day way? And that's why we have this new working group. And yeah, I think we see tomorrow morning further how to shape that, how to get started. It will take a bit of a while, but I think, you know, within 1.5 years until next AgMIP meeting, I think we can show results. And that's a challenge, and see then how we can approach communities that are not yet in, thinking of, you know, capacity building and many activities that we could do. Thank you.
So I don't think we don't have time for questions now. We're gonna keep moving. So we're gonna keep moving, and luckily after this session is lunch, so we can talk to the speakers after that. But let's invite Lisa up now. We're gonna hear from Lisa Emberson on characterizing losses in crop and livestock system models.
Okay, thanks very much, Alex. And I just wanted to start off by thanking the AgMIP Organising Committee for allowing me to talk on this title, but specifically focus on the hidden threat of air pollution. So really what I want to do with this talk is raise awareness, hopefully within the AgMIP community, about the impacts that air pollution is having on agricultural crops in particular, and some indication that it might also be having some effects on livestock. And then also think a little bit about how AgMIP might actually be able to help our air pollution effects community to understand what those impacts might be in a better way. Okay, so I thought maybe I'd first start off by mentioning this report that was released 5 days ago, so it's quite timely, by the UN. This looks at a report which summarizes the efforts that are underway to try and reduce air and climate pollutants. So one of the key things about these air pollutants that I'm going to talk about is that they're also climate forces. So they also have an impact on regional climate. So as well as having that direct impact on vegetation, they're also able to alter regional climate and will have an impact on vegetation that way. And this was a report which came out for Latin America, and it shows that by taking certain interventions to reduce these climate pollutants, we can see a whole range of benefits. We see benefits in terms of numbers of premature deaths that are avoided. We see benefits in terms of near-term climate change that is avoided. And the key thing, I think, for this community here is that we see benefits in terms of the estimated tons in yield loss of soybean, maize, wheat, and rice that would be avoided by bringing in these interventions. And these, I think, are quite large numbers. So I think this hopefully shows that considering air pollution would be a useful thing to do within this AgMIP community. Oh, so who said this worked? You jinxed it. Okay. Am I going backwards or are you going backwards? Right, thank you. This is going to be fun. Right, so the key thing that I also wanted to say with this is that if you look in the IPCC 2007 and 2014 reports, they identify the fact that ozone and climate change together will be impacting on crop productivity. And they also call for the fact that we need to have different approaches to doing the modeling. We need to be able to start to think about nonlinear effects of air pollution, climate change, nutrient and water availability to understand both the scale and the magnitude of the impact. So this is what I really think that working together with the AgMIP community, we can try and achieve. Okay, I'm going to try and go forwards again. Too tentative now. So I'm going to talk about two of these climate pollutants. The first is ozone, the second is going to be aerosol. This just gives an indication. You see up here there are chambers. This is how we get an understanding of what the impact of ozone is on vegetation. We basically grow plants in chambers for a growing season at different levels of pollutant exposure. And what we find is that we have visible injury, you can see here, for beans being grown in China. We get biomass losses, we get crop yield losses. We also get a number of other physiological and vegetation characteristic changes. So we have effects on photosynthesis, tomato conductance, transpiration, leaf area index. Not just yield losses, but we also see changes in the quality of crops. So for example, nitrogen content. We can see effects on carbon allocation, reproductive ability. And as I mentioned previously, ozone is the third most important greenhouse gas. So you're also going to get effects in terms of regional climate change if you have high levels of ozone in the atmosphere in a particular location. Then aerosols is the second pollutant. Some of the effects that we might see on crops here would be brought about by a reduction in the incoming solar radiation as it hits the aerosol particles in the atmosphere. So this can be called dimming. You also get a change in the quality of the radiation that's coming in. So you can get this increase in the diffuse radiation fraction, which people believe can lead to an increase in photosynthesis. And then aerosols can also cause warming both in the atmosphere and at the surface. So you're also going to see a change in terms of regional climate. And the thing that I haven't mentioned on this is that aerosols deposit onto the leaves. And so if anybody's been to Asia, then you just look outside of the vegetation there and you see really thick layers of dust deposited on the leaves. And we really don't understand what the impact of that is on plant productivity. Okay, and that's, yeah, just emphasizing that regional climate change impact. So there haven't been very many studies which have looked at these pollutants together. We tend to look at them individually. A fairly recent study by Bernie and Ramanathan in 2014 looked at the combination of both aerosol and ozone pollution across India. And they developed a statistical regression model which looked to see if it could understand the changes that you were seeing at the state level in terms of wheat yields in relation to weather and those two pollution variables. So here you can see for wheat, in blue, you have the effect by different states in terms of yield losses caused by climate, and in yellow, you see the impact caused by pollution. So we're seeing that already today, some of those pollution losses are far outweighing the climate losses. Now, I think this kind of study needs further evaluation. There are some really big losses being shown here, and we're not completely confident of those, but I think it does suggest that this is something that really is important to consider now and in the future. Okay, and then I also just wanted to, seeing as we're in Latin America, just make it clear that already there are systems that are out there to try and adapt to some of these pollutant impacts. So this is an early warning system for ozone, which is in Cuba and has been in Cuba since 1992. Essentially what we have here is ozone concentrations over a period of time. If they are seen to be particularly high, then the farmers will get a 5-day warning of when those high ozone concentrations are coming and be asked to withhold watering. So if you withhold your irrigation, then your stomates will tend to shut, which will reduce the amount of uptake of the pollutant that you get and hopefully reduce your damage. And they found that to be quite successful in terms of reducing damage to a number of crops. I think that it's also the case that if farmers don't actually take any action and then they try and make an insurance claim, that insurance claim will not be honoured. So this is having quite far-reaching implications for farmers and livelihoods. Okay, so just coming back to what are the sort of key concerns of some of these pollutants. We know most about ozone, so I'm going to focus on that in the coming slides. One of the main concerns is obviously the yield reductions that we see. This gives an idea of where most of the production losses for wheat, again, due to ozone, are seen across the globe. We can see hotspot areas, if you like, in the Midwest of the US, across Europe. But then more recently, we're really starting to see increases in South Asia, Southeast Asia, and East Asia. And what we found within this study is that it tends to be the humid and irrigated locations that are likely to be most at risk from ozone impacts, because those will be the locations where you have ability of the ozone to be taken up by the stomates and actually cause damage. And we see quite large global annual economic losses in the region of about 25 billion US dollars. So again, this is something that's a problem currently today that we need to be thinking far more about. Other issues that are affected, so it's not just yield. Ozone has been shown, so we've got an increasing ozone concentration here, and we've got a reduced nitrogen fertilizer efficiency. That can be due to just reduced uptake through the roots, as well as alterations in nitrogen remobilization within the plant. We also see that ozone can impact drought tolerance. So you have, under clean air conditions, you have the drying soil, releases ABA, which is sensed by the stomates and leads to stomatal closure. If we have an ozone polluted environment, then that ABA signal is prevented from being sensed by the production of stress ethylene. And so we can have sort of leaky stomatas that can actually enhance the amount of water that's lost. We also see that ozone can decrease the amount of root biomass. So the plants are just less able to actually access water in the soil. Forage quality, so this is really just to show that two ways in which ozone can affect forage quality, so therefore affect livestock. Firstly, we can see a reduction in the clover fraction of grasslands, so grasses will tend to outcompete legumes, which will reduce forage quality. And then also we see that ozone reduces nitrogen fixation in many of those legume species. So you'll have less clover and you'll have less nitrogen in the clover under ozone conditions. And pests and diseases, we can see here that with increasing ozone concentrations for a sensitive plant to ozone, indicated by these the closed circles, then we tend to see increases in pest reproduction. So here, red spider mite as an example. And we have a session in AgMIP looking at some of these issues. So one of the questions that we might have is, what is the contribution to the yield gap of ozone in relation to some of these other constraints to yield? Unfortunately, I don't have results to show you that, although there is work that I've been involved with, which has been going on to try and look at this. But just to show the kind of other constraints that we have, this is a slide which gives an indication for the percentage of the yield gap that you have by different region. We can see constraints of water, nutrients, pests, weeds and diseases, mechanization and knowledge systems. And this is just to emphasize that pests and diseases, for example, across all of these regions are giving quite substantial contributions to reducing that yield gap. Okay, and there is some uncertainty in terms of making these assessments because of how we actually make those yield loss estimates. So some of it is based on yield observations versus expert assessment, and there's a big variation between those two estimates here shown for both maize and potatoes. So there's more work that needs to be done in terms of that yield gap analysis. So coming back to air pollution, just to say and show that this is a problem now, it's going to be an increasing problem in the future. Here we show surface ozone changes, so from 0 out to 2050. And I just want to identify these two areas here, South Asia and East Asia, which are already showing really quite significant impacts. The emission projections would suggest that the ozone concentrations are likely to worsen in the future in those regions. And just one other thing to mention is the fact that in the future, we also are concerned about the fact that crop breeding is actually making crop cultivars more sensitive to ozone pollution. So here, data for soybean is showing that the year of release of these different varieties, this is a dose response slope function. So as you have negative numbers, then your crop cultivar is becoming more sensitive to ozone. So you can see that as we release newer varieties, they tend to have a higher sensitivity to ozone pollution. So this combination of impacts is something that needs more investigation. Some quick insights in terms of SDGs. I've just come back from a workshop in Kathmandu where we were talking about air pollution and SDGs and highlighting the fact that actually there isn't an SDG for air pollution, and is that a bit of a problem? And I think for people in Asia, it probably is actually, because as well as trying to make sure that they meet their commitments to SDGs, they're also trying to prevent people from dying due to air pollution. And there are some trade-offs in some of these SDGs, which are important for those policymakers to consider. If we're thinking about trying to reduce the impacts of air pollution on agriculture, then obviously we can either mitigate or adapt. If we go down the mitigation route, then we would be helping in terms of goal 2.4, in terms of zero hunger, because we would be improving crop productivity with less air pollution. There are sort of trade-offs in relation to the SDG on climate action, because in some situations we still don't really understand what the aerosol impact is on crop productivity. And we also have a situation where if you reduce all the aerosol, you take all the aerosol out of the atmosphere, then you actually might see an enhancement of climate change. So there are trade-offs that need to be understood there. And then obviously, if we have mitigation through pollutant emissions, then we can also help things in terms of human health, energy access, and other issues in terms of SDGs. What role can AgMIP play? What I really want to show here is the fact that we can move from this very simple empirical dose-response relationship to a better understanding of the processes which are leading to pollution impacts. And just quickly, I know I'm trying to speed up. So this is my schematic presentation of the Farquhar model. So this is sort of thinking about crop models that might actually be based on Farquhar photosynthesis. Got light reactions here, dark reactions, carbon assimilation, giving us gross photosynthesis, and net photosynthesis, less or dark respiration. And then if we couple this to stomata conductance, then we can have water loss coming out of here. And importantly, we can have the pollutant ozone uptake so that we can get an estimate of the dose and therefore the impact. And I just wanted to show here with these flashes, there we go, of different pollutants, how you could use this kind of process-based approach to really understand the impact that aerosols, that elevated temperatures, heat stress, ozone, nitrogen content through nitrogen deposition, and elevated CO2 concentrations could actually all be brought together to try and get better assessments of impacts. So we have AgMIP Ozone Initiative. Just to run through quickly what we're doing here, we're collating and standardizing fumigation data sets. We've identified a number of ozone crop modelers already. And we are going to hope to use those fumigation data sets to develop and evaluate crop models. Then we would be developing crop modeling protocols so that we can apply those crop models at a global scale, conducting model ensembles to try and assess the benefits of different emission pathways. And through that, develop advice for policymakers in relation to food supply, both mitigation and adaptation. And this just gives an indication of the standardization of the different fumigation sets that we have already. We've got somewhere in the region of 21 data sets that we can use. And the final slide is just to give a suggestion of how this kind of activity could actually help to connect with other global initiatives. So we have the UNECE Long Range Transboundary Air Pollution Convention. Part of that is ICP vegetation, looking at ground surface, on the ground biomonitoring. And then we also have hemispheric transport of pollution, trying to understand how pollutants are moving around the whole hemisphere and impacting in different locations. We have AgMIP, which is trying to understand regional air quality modeling and evaluations, and see if you can spot the person that is in the room that knows about this. And then we heard a lot this morning about AgMIP 6. And then finally, just to take 30 seconds more, just to mention this Climate and Clean Air Coalition. So these are really the people behind that first Latin America assessment that I showed at the beginning. And they are working with countries to develop national emission reduction plans and INDCs. So there's an opportunity there, I think, for AgMIP to really come in and help in terms of the trying to reduce the impacts of air pollution on agriculture. And that is it. Final slide, just to say thank you to all the people that have also been involved in this. Thank you.
All right, thank you, Lisa. We're going to keep going, so I'm going to invite Jean-Francois to come on up. We have 2 more talks before lunch, so please keep your attention up just a little bit longer. Jean-Francois.
Thank you, Alex, and sorry for keeping you waiting for your lunch. But I'll try to address the mitigation issue, really. We will see that there are some approaches that can be grounded in AgMIP and can be used for those challenges. But let's go back to the main challenges, really. Now we have an international agreement that targets stabilization of climate within 2 degrees Celsius warming. The point is that there is an aspirational target from the work of cross-sector models of 1 gigaton CO2 equivalent mitigation, as you can see here with the blue bars from a range of those models. It is about 1 gigaton that we need to abate. And however, the technical practices that are available at moderate price, at moderate cost, for nitrous oxide and methane mitigation provide only 20 to 40% of that target. So we are not going to reach the target unless possibly we can use other options. And I was pointing in this slide to the possible role of soil carbon sequestration. However, soil carbon sequestration is not considered so far in most of those integrated assessment models, such as GloBiome. So we made an effort with YASA, with this GloBiome model, to test the potential mitigation, this time for the agriculture, forestry, and land use sector. And you see that by 2050 for that sector, to reach a 2 degrees Celsius target, we need to have a global abatement by about 6.5 gigatons CO2 equivalent per year. And if we need to reach the 1.5 degree target, it would be even 8 gigatons CO2 equivalent per year that we need to abate, so very large numbers. Indeed, when we look at the traditional mix of options to do this, we find that afforestation, that is a green bar, forestry and land use, is achieving most of the mitigation in the mix. The agriculture with the agricultural methane, which is here, and with the nitrous oxide here, is relatively small. So the question was, can we introduce soil carbon sequestration in that mix of options? So we did this using the IPCC mitigation abatement cost curves for the soil carbon, and they were introduced in the model. And this led to adoption of those practices since they are cost competitive, and they actually tend to double the potential from the agricultural sector. Then we said, okay, there is also a co-benefit because with more organic matter in your soil, you may in fact increase yields. So we took a conservative estimate of this yield increase with increase in soil organic matter. And this is now this SOC plus, soil organic carbon plus, with the yield effect. So you can see some reasonably good adoption of this soil carbon, especially when you consider a positive effect on yields. And it is quite important to read on the right scale now, these triangles, because they read to the calorie loss per capita in developing countries that is caused by the mitigation policies. So this goes back to the previous talks that were showing how mitigation can create a burden on food security. And in fact, this burden is really intolerable. We cannot accept that there would be a 300 plus kilocalorie loss if we reach a 1.5 degrees Celsius target. It's impossible. So the good news, however, is that introducing the soil carbon in the mix of options allows to reduce by at least 2/3 or even more this burden on food security by reducing the global calorie loss down to about 100 kilocalorie per capita in developing countries, which is not good, but is at least slightly better for the 1.5 degrees Celsius target. So I think that's a bit the context in which I'd like to present some more technical studies, because while we have been doing this, we certainly realize that these are extremely coarse estimates of the greenhouse gas emissions and of the potential of abatement. We need to have far better estimates. So this was done in the context of the Global Research Alliance on agricultural greenhouse gases, which has 49 countries. You can see here's a list. There was a map somewhere, but here it's coming. Okay, and this is a structure of the Global Research Alliance, which is governed by a council representing the countries. It has 4 research groups, 3 sectoral research groups on paddy rice, livestock, and croplands, and an integrative research group where I'm a co-chair with colleagues from Canada and Australia. And we are strongly supported by a secretariat, which is funded by New Zealand. So this integrative research group structure really goes by scale. We start with the soil carbon processes, then we enter into the field scale, in the farm and regional scales, and there we have the integrated assessment models for the regions, but also some farm models. And we have also the greenhouse gas inventories. And you see the 2 key areas of interest for the countries, which are about the soil carbon. They want to have this soil carbon sequestration implemented. That's why we developed a flagship project. And there is also an inventory flagship project because we need to improve the greenhouse gas inventories. This is also a strong demand by countries. So let's go back to the field scale network, because this is where we had strong interaction with AgMIP. It is structured with internationally coordinated modeling activities. And we started by comparing an ensemble of models, which are in fact biogeochemical models, simulating greenhouse gas emissions, yields, and soil carbon stock changes. Then we also tested these models for their sensitivity to climate change drivers. We've been also comparing more specifically the soil models using long-term bare fallows, because that's where you can really test the soil models. And we've been entering into that discussion on how you represent with models these mitigation options that are needed for the future. Okay. Let's go back to this ensemble modeling of the greenhouse gas emissions, yields, and soil carbon. We got 24 models from 11 countries, and we've been using 10 contrasted sites, 5 grasslands, and 5 arable crop rotations. It may be interesting to underline that we decided to have not only biogeochemical models, but to apply those models to crop rotations, to have no soil reinitialization, so we are really running the study with the changes in the soil conditions, and to compare obviously multiple variables, as you understand, since we're addressing both the yields and the N2O, for example. So in the first paper, we could show a sort of highlight that the median from an ensemble of crop and pasture models is able to predict within experimental errors the nitrous oxide emissions. So let's go back to the details of this. Here are the sites for the grasslands and the croplands. They span a rather large temperature and precipitation space. And this is the design of the study. we started with a blind test, so uncalibrated models that were compared. Then we had partial calibration, delivering to the groups the history of the management of the fields, then delivering some vegetation data, some soil data, and finally we got full calibration of the model after providing the emissions and the yields. So as we know from AgMIP, but this also applies to the nitrous oxide emissions, when you look at single models, you are not so successful initially, at least. With the blind test, which is stage 1 here, we have a small fraction of the models that perform within the experimental error. If we go to the nitrous oxide emission in some species, it was quite good. And actually this was with maize and with the pastures. With others, it was really not the case. And if we combine the constraints of being within the experimental error for yields and nitrous oxide emissions, you see we have a relatively low fraction of the models performing correctly. So the good news is that the E median, the ensemble median deviation to the observed means and standard deviations, which are plotted here as a gray band, at least for the nitrous oxide emissions, are relatively good. So we are able, quite usually from the start, to simulate those emissions within the experimental error. There is one exception here, and frankly speaking, I need to check why this site was off, but there was a reason, I think. And for the yields, it improved after providing the phenology. Those models we've been using, the biogeochemical models, are maybe not as good as the ones you have in the wheat activity. And we need to provide crop phenology to get them really working. This could be improved, I guess. As you see, for the grasslands, it did not really work. There are 2 sites where we were never able to simulate correctly, even after full calibrations, the productivity. Grasslands here are grazed grasslands. And you know, even measuring the productivity, above ground productivity of a grazed pasture is quite difficult. So we suspect that models may be wrong, but the data can also be to some extent wrong. So to conclude on this, under realistic conditions with crop rotation, grazed pastures, no soil reinitialization, we got robust predictions of the yields, but only when the phenology data were provided. This is with the ensemble medians. Grazed pasture productivity is still uncertain, both from experiments and models. Nitrous oxide, yes, we have some good results with the model ensemble medians. And what is quite nice is that a key variable in terms of what you want to achieve, which is to reduce the nitrous oxide emission per unit yield, we call it the yield scale nitrous oxide emissions, they were ranked accurately by a small ensemble of models, an ensemble of 3 models. So here's a perspective would be certainly to have a platform with those 3 models and run it through to see how you could get predictions. We went further in trying to assess the structure of the models and its possible role on the performance. I will not enter into the details. There are many different ways to represent the carbon nitrogen cycles in models, and you want to relate the different approaches to the model weaknesses in terms of the processes which are represented, but also representation of the pedoclimatic variability. And here we have another paper that is now under review, where we enter into the mitigation options. So with the same grassland sites, we've been testing mitigation options like halving the animal stocking density. As you can see here, if this works, as you can see here, the animal density is halved. And here we suppress nitrogen fertilizer and we keep that reduced stocking density. So we move from having a small carbon sink on average. This is the deviation is across the model ensemble, and having rather high nitrous oxide emissions to a situation where we have a large carbon sink, because with less animals, you have more returns of carbon to the soil. And obviously with no nitrogen, you reduce strongly the N2 emissions, the N2 emissions here. And for the methane also, it would be reduced. I didn't draw a bar for the methane because not all models were simulating the methane emissions. And that's just a brief example also on what we do on a smaller scale, which is really the soil models. as I try to explain, what is nice is that with a bare fallow, you can test the properties of soil models because you do not simulate the inputs. There are no inputs, so you just look into the decay of the organic matter with your slow carbon pool, which is decreasing, and the stability of this pool, which is supposed to be quite stable. So I didn't show results here because they are not yet fully there, but actually the models mostly work quite well. And the last example I'd like to take to show similarities with the approaches, and this was really developed within AgMIP. We performed with it the AgMIP test for temperate grasslands, those scenarios looking at climate change drivers effects, not only on the productivity, but also on the emissions of nitrous oxide and on the soil carbon. And I will not have time to enter into the details, but you know, we can use those emulators and they actually perform quite nicely. So this just brings us to the understanding that a lot of the pioneering work which has been developed under AgMIP is actually readily applicable to this issue of mitigation. And we can bridge across scales. What I've been showing here was field scale, but we certainly want to upscale. And what was shown by Christopher on the global grid, it could actually be applied, as I think you mentioned, to those nitrous oxide emissions. It would be this example would be of high interest for countries because some countries already have some tier 3 inventory methods which are based on models, but we could certainly move into that direction. And combining mitigation, adaptation, and productivity would be essential, I think, in the future. Thank you.
All right, let's keep on moving on. Thank you, Jean-Francois. Herman is next to speak. And I believe we do have 1 or 2 quick announcements after Herman's talk, so don't run out the door right away. Herman, global economics, shocks, and regional trade.
Yes, thank you. Knowing that I'm in this terrible situation between you and lunch, right? So I'm trying to be quick, but of course I forecast this and didn't put together too many slides, and I will expand a little bit on the global economics results I discussed yesterday a bit already. So let me list a few outputs of the global economics teams recently, and I put in green issues which are related to some institutions which are relevant. So for example, out of phase 1, we had a book chapter focusing on trade results. And by the way, I had to change my title a bit because I'm not saying much on shocks, a little bit on trade, and shocks will be my last bullet point on the last slide. So we had one book chapter which discusses some trade results, which I will show. And then we had a paper in 2015, which came out of a USDA-funded project. And then we had these 2 smaller projects which were JRC funded. So JRC is the Joint Research Center as part of the European Commission, which shows a bit that we were able to generate at least limited funds for getting this work going. And actually the scientific papers out of this is actually then the follow-up from these little projects. So out of the JRC science policy reports, we are now have one paper van Meyl et al. In ERL accepted. So that's, I think it's already out there. 2 papers with Nature Climate Change in revision. I won't show any results from those. And some other things either in preparation. So this decomposition study, that's actually a technical study, which is a bit delayed, where we explore the technical sensitivities of the models for specific shocks. That's a bit delayed, but we are also working on that. Plus, the data is openly provided from most of these activities in the JRC Data M portal. So I think we can show quite some support from relevant institutions, which is also relevant for our stakeholder discussion, of course, in general. So I'll go through a few results, sorry. And I also want to link to the inputs we are getting from the global gridded crop model. So very briefly, this is our current scenario framework. So basically, we are looking at 3 SSPs and then 4 different types of scenarios, a no climate change reference run, kind of a full climate change impact run, a full mitigation run in line with the 2-degree stabilization target, and then full mitigation plus the residual climate impacts. And this was kind of our minimum scenario matrix. And then we were thinking of how to reduce the number of single scenarios to be run. Being economists, our colleagues said, you know, we are only doing as much as needed and not running like hundreds of different scenarios unless we are forced to do extensive sensitivity analysis. So we needed to think about it. And we're of course faced with the problem that, well, we wanted to cover at least 3 crop models here, like APIC, LPGML, and PDSET from our GGCMI colleagues, and then different RCPs and with and without CO2 fertilization. So this gives you at least 15 combinations, crop models times GCMs. And in principle, of course, in each of these matrix cells, you could run all of these combinations. And together with our colleague Christoph Müller in the orange shirt back there, we came up with a neat method to look at the crop model GCM combinations and look at which of the combinations it represents best like the median in the aggregate global results, and then saying to the economic modelers, okay, if you only want to run one scenario for each of the cells, then we advise you to take this median, and then we would have plus minus 1 standard deviation to reduce the number of runs to do some sensitivity analysis. There are also some disadvantages with this method, which we could discuss, but it worked fairly well. So that was a nice cooperation, again, with our global gridded crop modeling colleagues. And then a few results extending on yesterday. So in this paper, which is currently out now, first of all, what are the effects on a greenhouse gas emission reductions, so the non-CO2 emission reduction. This was the new figure or feature we put into this paper. And what you can see, we have the 2 climate impact scenarios, and this is all in 2050 relative to the baseline. And so we actually, and then 2 mitigation runs with and without the residual impacts. And you can see we are actually really drastically reducing non-CO2 emissions. So that was, of course, the key of these mitigation scenarios. It basically includes increased biomass demand, bioenergy production, plus taxation of non-CO2 emissions. And this has then effects on agricultural production. Of course, agricultural yields and production are reduced due to the climate impacts, and you see the different effects here. This is all in percentage change compared to the reference. And in the mitigation cases, the reduction in agricultural production is actually stronger because there is more competition for land due to increased biomass demand, and also effects of the mitigation of the emissions. So this is the combined effect. So the reduction in in prices is also then linked to changes in land use. And what we can see here, and of course in the detail, we can also then compare always the different SSPs. And what we see, for example, with respect to cropland and in SSP3 with more restricted trade, we have a stronger expansion in the land use compared to the other SSPs. And with the ambitious mitigation, cropland for agricultural production is reduced because of this competition with the bioenergy production. And similar results for grassland, which is also covered here. And then I discussed yesterday the final outcome in terms of prices, and that with this analysis we see stronger price increases relating to all these changes in the economic models with respect to mitigation, and actually the strongest effects in the SSP 3 compared to the climate impact runs, where by 2050 the increases in prices are rather modest. And of course, there are several effects with this. One thing we can also compare here between the different SSPs is that diet change in terms of reduced meat consumption is not part of the explicit mitigation strategy, but we see here that in SSP1, of course, there is a different trend in diets with reduced meat consumption, for example. And this is part of the effect of the lower price effect. And this is also necessary to discuss once we are going into the implications for the overall mitigation strategy. Listening to the talks by the regional economic modelers, I think one aspect further to be discussed is, of course, so what's the impact of these higher prices? I mean, if we now look into food security implications, the current relatively simple approach is, okay, you have higher prices, demand is reduced, and this increases the number of people at risk of hunger. So that's the method we are currently using. But it's, of course, more diverse because higher prices for potentially food insecure subsistence producers may actually be a good thing. And we need to look more into the detailed effects, what actually happens on the ground. And I think here we can and we should cooperate more with our regional modeling colleagues to really get an idea of what's the effects. But we are getting there step by step, I think. We also see quite a wide spread across the models. I'm not discussing that now, but we see the benefit of having this multi-model approach also with the economic models, because also on the demand side, you can see, and this is shown in the prices, that the range between the models is actually quite large, and we are exploring the reasons for that also in this comparison exercise. And then very briefly on trade. In this current exercise, we haven't really looked at trade, so I pulled out a few or two slides from this study, or the book chapter from this FAO publication from phase 1, actually, where we looked at changes in agricultural trade for certain regions. So, for example, net trade in rice for India, or net trade in wheat for sub-Saharan Africa. This is a slightly different scenario set up. And you see here that, well, in some cases, for example, net trade in wheat, the different models agree quite well that imports are actually quite heavily increased in sub-Saharan Africa for wheat. That actually the climate impact scenario, which is the blue ones here, don't make such a big difference compared to the reference run. But we also see in other cases, it's here for India, for example, that there's quite a disagreement across models. So with respect to trade and the regional trade position, the net trade position of important regions, we need a lot more work. And for the current runs, we haven't really much looked into this. And another example, if I can get there, is rice in sub-Saharan Africa and coarse grains in sub-Saharan Africa. And again, you see here for coarse grains, for example, quite a disagreement within the models, and also no real additional effects from the climate impacts. So this is actually first steps towards understanding better what all these combined effects mean for the net trade position, self-sufficiency rates, etc., for our modeling region. So this is certainly one area we need to explore further, but we took it step by step and not overburden ourselves with too many aspects to cover. But in principle, of course, these results are there and could be pulled out of these models. So that was very quick, but I encourage you to look at these publications. As I said, most of them are openly available. Otherwise, get in touch with me and I can point you to them. And over the last weeks and months, and also yesterday, we started to discuss what are next steps on our agenda. And so one aspect would actually to evaluate in more depth the regional results for sub-Saharan Africa, South Asia, and Latin America of the different elements, as I showed. Looking at the health implications from production and consumption changes, and we are already in discussion with our health colleagues how to do that. So we have the methods, and we could just do these post calculations. where we want to look at integration of multiple climate impacts beyond crop yields, and we can also do that, and we'll push that forward with a new funding call on the European side. We need much more to look into wider range of mitigation options and policies. And I already added the soil carbon management aspect because we yesterday discussed with Jean-François. There's many aspects to it which go beyond what I showed today, explicit implications of diet change, potential compensation payments. I mean, if you tax non-CO2 emissions, that has a direct effect on prices. But then if you use part of that tax revenue to recycle and transfer to poorer income groups, then this can, of course, mitigate the food insecurity aspects. So there are many more details we could also try to assess with our models, at least in a qualitative way. Better linking of the global and regional models. I think we have some proof of concept, but it's not so easy as we thought. But I think there's obviously benefits from cross linking here. And of course, we also need more differentiated assessment of food security impacts, because it's not just like higher prices, more food insecurity. It's more complicated, and we need to work on that. Finally, in gray, the shocks, the short-term variability, and the storage. Yeah, this is, of course, the big deal. At the moment, I would say this is not quite the topic for our multi-model ensemble run. I hope, and some of the modeling groups are working on new approaches, extensions of their models to get to grips with these aspects. But I think it will take a while until we really will cover this in this kind of multi-model approach. And I hope, we discussed that 6 weeks ago in our workshop, that at least one or two of the models will come up with an approach to tackle that, and then we can bring that into AgMIP as well, but it's a longer term endeavor. And that was my presentation. Thank you very much for your attention.
All right, thank you, Herman and Jean-François. I know that you were facing a short time, and I appreciate that. All right, we're about to head out. I do have one quick message. Everybody from the CGIAR system, please hold here for a couple extra minutes before lunch. There's a planned short meeting. Also, if I could ask you to please pull up the abstract. There was the document that I pulled up. And Carolyn, do you have a slide on room change information? Maybe not. So just be, okay. So there is a slight change in the rooms for their parallel sessions this afternoon.
Overview to what was in the detail. So as you go out the door, we have a printout for this afternoon's sessions that has consistency with the overview. And you will, we also have a talk that has been inserted that was inadvertently omitted. So Alex, is that what you're referring to?
Yeah, so that's the one other announcement. Okay, so this is this slide. If I could ask, please just show that Word document fast. And then there's another Word document that I dropped on the desktop. There was an abstract that was submitted that was inadvertently left off the program, and I want to make sure we mention it quickly.
So while that's coming up, just a reminder that all of the abstracts for all of the sessions are available on the ECA website. If you go to the link that was provided, there's a new tab that says abstracts here or something like that in bright green. Amanda kindly concatenated all of those, and I think we still have to add the one that was left off. But yeah, you can find all the rest of them there.
All right, I think I just did want to briefly mention there's a talk by Peter Van Evelen and Roy Rasmussen on some next generation climate products and the possibility of deploying those in the Andes region. And suitably, that's going to be in the Andino room this afternoon in session 2C. So please check that out if you're interested. All right, and then maybe we leave that slide with the sessions and we are dismissed for lunch. Thank you so much.
Yeah.
Yes.